Good day, ladies and gents. My name is Latabu, and welcome to my recap series. Um, I think we need to start this with a prayer, if that's not much of a problem for you guys. So let's go. Heavenly Father, thank you for blessing us with the ability to see, to hear, and to learn. Thank you for re-energizing our souls and comfort those that are in states of depression, of anxiety, those that are not, I would say, okay in their current spaces in life. Help them rejoice, help them feel happy, help them learn, focus up, Almighty Lord. For there is nothing you cannot do. In your name I pray, amen. So yeah, I think it's good if we were to start us with a prayer. Today we are doing limits. Yeah, which is one of the many things we did today. But we're doing limits. So what are limits, one would ask? So limits limits mean they're used to show how a particular function behaves as we approach a particular value, right? So those are limits. So basically, in this sense, let me have a parabola here, something like this. X, Y, 0. So they are to basically show, let's say, what would happen to y, to the function. Let's say this function is x squared, even though it does not resemble x squared. Let's just say this point touches 0. So if I was to limit this function as x approaches infinity, then what happens is x goes towards infinity is y, or the function itself goes towards infinity, right? So something like this. So in the most basic sense, that's what limits are for. That's what limits are. And limits only exist if the limit as x approaches, let's say, that particular value. I'm going to say a from the left of f of x is equals to the limit as x approaches a from the right of f of x. Right, so this is the only time a limit will exist. Right, yeah. Let me see. So yeah, basically if the left hand limit and the right hand limit exist, so now it's going to limit laws. So the laws of limits are quite basic. So the first law goes something like this. Limit f of x minus g of x, or minus or plus, let's say, as x approaches a, then we could deal with these separately by saying limit f of x as x approaches a plus minus limit g of x as x approaches a. So basically one could say distribute the limit within the brackets, but that might be wrong terminology when it comes to mathematics though. So the other rule is limit c times f of x as x approaches a. Then in that case the constant stays aside. You could say limit f of x as x approaches a. So that's a rule. The third rule is limit f of x times g of x as x approaches a, which we could deal with them separately by saying limit f of x times, limit f of x as x approaches a times limit g of x as x approaches a. And then the other one is limit f of x all over g of x as x approaches a. Then we'll have limit f of x as x approaches a all over limit g of x as x approaches a. So we're putting limiters on them. If limit g of x as x approaches a is not equals to 0, then 5. So limit f of x to exponent of n as x approaches a is equals to limit f of x as x approaches a all to the exponent of n, where n is an element of positive integers. And then 6, limit c, which is a constant, as x approaches a is equals to c. So it doesn't change that much. 7, if we're to limit polynomial, right? Whether it's x or x squared or x cubed, whatever polynomial there is, let's say x to the exponent of n, then we just substitute the value we're limiting towards inside the polynomial. So it will be a to the exponent of n, where n is an element of all positive integers. So yeah, that is it. That's that. When it comes to limit laws. Actually, there's more. Let me write them all. There's 8. It goes something like this. Limit as limit the nth root as x approaches a. This will be equals to a to the nth root. Then, provided n is an element of all positive integers. And number 9, limit f of x to the nth root as x approaches a. Then this will be equals to f of a to the nth root, provided that this is a polynomial, or to respect mathematical laws, equals to limit f of x as x approaches a, right, to the nth root. And then for number 10, if we have, let's say, limit a to the exponent of sine x over x as x approaches b, let us say, then this is equals to a limit as x approaches b sine x over x. Right. Yeah. So those are all the limit laws we have. Yeah, are all the limit laws we have. So make sure you wrote these down or committed them to memory, because we are about to do questions. Maybe not. Let's see. So, given the following, so the question is evaluate limit as x approaches pi over 4 x squared sine x. So how would one do this? Well, you could separate it for starters. Limit as x approaches pi over 4 x squared multiplied by limit as x approaches pi over 4 sine x, and sine x is a polynomial, x squared is a polynomial. So what do we have? We have pi over 4 squared times sine pi over 4, which sine pi over 4 is 1 over root 2, so also over 2 over 2, 2, 2. So therefore we have the following. We have root 2 multiplied by pi squared all over 32. So yeah, that's what we have. You could try the question alone in your spare time. Joking. Like, you could pause the video and do the question, then you'll see our evaluation at the end. And now let's do question number 2, which is limit as x approaches 0 of x squared sine 1 over x. You could apply the same thing here, like separate them and then find the limits of each. But notice that when we substitute 0 into sine 1 over x, we get, I like to say infinity because 1 over 0 should give us infinity. 0 should give us infinity. This comes from this function 1 over x. As this function approaches 0, it goes towards infinity. So yeah, you could also see this when you are putting 1 over, let's say, 0.0001 and increasing the number of zeros. You'd see it will be larger and larger and larger number. So that is why that is said to go to infinity. But now, in this case, we are going to use something called the squeeze theorem. So what we know, right, to be true is that sine 1 over x is between -1 and 1. So that's true, right? Sure. So if we multiply everything by x squared, what we would find is this, right? X squared, negative x squared is less than x squared sine 1 over x, which is less than x squared, right? So that's what we got. Right? So now note, if the limits of this and this are equal, then they should be equal to the limit of that. So that's the squeeze theorem. So let me repeat it. If the limit of this and the limit of this are equal, then they should be equal to the limit of this. So let's find the limit of the first one, which is this. So limit as x approaches 0, negative x squared. So that will give us what? 0, right? And limit as x approaches 0, x squared. That will give us 0. So therefore, limit as x approaches 0, x squared sine 1 over x is equals to 0. And you could say squeeze theorem. Squeeze theorem. So that's that. Commit that to memory. Work on it from time and time in, time out. Yeah. Make sure you understand that part. It's very important. And then number 3 says limit as x approaches 2, x squared minus 2 all over x plus 2. So what we are going to get here is let me substitute just to show what we're going to be getting 4 minus 2 all over 2 plus 2, which is equals to 2 all over 4, which is equals to 1 over 2. So that's that. So what we getting this and this and this. So that's our solution. And moving on to the next question, we have 4. Limit as x approaches infinity, x cubed plus 3x squared plus 1 all over x cubed plus x squared. So what I predicted is 0, right? But it's not quite 0, and it's not 0. So the trick one could use here, let me see, is you could substitute the infinities. Infinity over infinity is indeterminate, right? So you cannot say infinity over infinity is 1, because look at this. You have infinity cubed plus 3 infinity squared plus 1 all over infinity cubed plus infinity squared, which is equals to infinity all over infinity. I know the answer. It's 1. No, it's indeterminate. Why is it indeterminate? Well, because infinity is like a very large number, right? In each case, it's a symbol used to represent a very large number. In this case, these very, very large numbers may not be equal. Right? So we cannot just say, it's 1, I know the answer, it's 1. Because we don't really know what the values of those infinities are. Right? So we need to solve this in a more basic way, more simpler way. So what we're going to be doing, right, is multiplying both sides by the highest power of the denominator. The inverse of it. So since we 1 over x cubed, multiply 1 over x cubed over 1 over x cubed. So what you will get is the following. You get 1 plus 3 over x plus 1 over x cubed all over 1 plus 1 over x, right? And then remember from this function, that's 1 over x, right? Anything over x, basically. As x approaches infinity, right, y approaches 0, right? So please note from this function. So what that means is you're going to have 1 plus 0 all over 1 plus 0, which is equals to 1 over 1, which is equals to 1. In this case, it is equals to 1, but it's not in all cases. know that is of paramount importance. But in this case, it's equals to 1. What can we do? Nothing. It's just 1. But in the following examples, it's not really equals to 1. I'm about to show you. Now? Okay. So this is the other example. Infinity x to the 4th plus 2x squared over x cubed plus 1. So we do the same here. X cubed 1 over x cubed, right? And what we get is limit as x approaches infinity get x plus 2 over x or over 1 plus 1 over x cubed. So we're going to get infinity plus 0 all over 1 plus 0. So our answer is going to be infinity. And then for the last one, I get limit as x approaches infinity x cubed plus 1 all over x to the 4th plus e, right? So do the same here, times x to 1 over x to the 4th, 1 over x to the 4th. So the limit as x approaches infinity, 1 over x plus 1 over x to the 4th, 1 over 1 plus e over x to the 4th, which we are going to get 0 plus 0 over 1 plus 0, which is equals to 0.